Hello everyone, today I will talk about our recent paper called Rectified Metric Propagation for Facial Learning. This is a joint work with Chuan from Microsoft Research and Ping Yu and Changyu Chen from University at Buffalo. Okay, firstly, introduction. The motivation of the paper is very simple. The fundamental task for the metric-based facial learning method is to design an appropriate metric space that can satisfy the following three properties simultaneously. Firstly, a valid measure such as Euclidean distance and the cosine similarity. Second one, a cost function that can fully exploit input information to update the neural network. And thirdly, metric consistency from training to testing, as well as from pre-training to fine-tuning if a pre-training is applied. While the first two properties have largely been individually explored, the last one is less studied, so the natural question will be, is there a strategy that can maintain the metric consistency, as well as fully utilize the training data information to learn the meaningful metric space? Let's first review the contribution. We identify the metric inconsistency issue between training and testing in facial learning, a long-standing issue of almost all metric-based facial learning approaches. To alleviate this problem, we propose a cooperative label-aligned training scheme where the unbridged metric space can be inherited to the testing phase. We also describe a contextualized label-embedded module containing alternative prototype propagation layers to take into account data importance to make more confident predictions. With the above two notices, new state-of-the-art performances on three standard facial learning classification datasets, the mini-IMNet, tire IMNet, and CFR-FS, are achieved. Let's first have a quick review of the preliminaries. Revisit the classify the feature space. Current approaches to facial learning resort to a two-step procedure, which is represented as a function decomposition, G and F, where F is a feature structure that maps the data to the feature space to the feature vector Z. G is a classifier, mapping the feature vector Z into a vector of logits Gz. Since F and G are sometimes not chained end-to-end, it is very crucial to find a good association between a classifier G and the feature representation Z. Typically, there are two general paradigms to design the classifier G. Unfortunately, both paradigms involve a limitation. For parametric methods, these approaches are usually learn a linear classifier Gz equals to WZ plus B, thus inherits fast convergence. Two solutions can be designed afterwards. Fine-tuning to adapt the parameter to test the sets, performing the nearest neighbor search in an embedding space for testing. The second one leads to inconsistency between training and testing. This is because Gz is computed based on a linear mapping in training, whereas the nearest neighbor is used in testing. Because in this paper, we only focus on the second one, that is the nearest neighbor search, which also achieves the state of art in metric-based facial learning. And for non-parametric method in training and testing, one consistently applies a metric-based similarity measure Gz equal to kappa Z and Cn, which calculates the similarity between Z and prototype Cn. Cn is a closed prototype. However, it has been found that these approaches are hard to explore and learn a dismantled metric space. Okay, let's go into the model description. In Figure 1, we illustrate the proposed label-aligned learning. The training considers matching in both a parametric global weight space. You can look at the top right. The global weight space that is, in summary, like for example, in mini-IMNet, there are 64 training classes. So in global weight space, there will be 64 different global weight vectors. And it also consists of a non-parametric rectified metric space, because we apply the episodic training. So we have a support set, we have a query set, and we have for NYK short, the local prototype space will be N classes, right? In testing, prediction only met through local matching in a feed-forward manner, where rectified prototypes have to generate a better decision boundary based on self-attention. Let's move into the detail. For level-aligned corrective learning, we firstly define a level-aligned learning objective to optimize the feature structure F and the classifier G in training. It completes the corrective learning on two levels, global matching on the global prototype of the chain, and local matching on the local prototype of the episodic S and Q. S is a support set and Q is the query set. The goal of global matching is to ensure fast convergence, and the goal for local matching is to close the gap between training and testing. For global matching is a parametric model aimed to make predictions matched with a global level. To this end, the global likelihood and the global loss are given in equation 1 and equation 2. Let's first review equation 1. It's a softmax function, and it calculates the similarity between the feature of X and the global prototype, the global feature, that is W. And we can calculate the probability that X is classified into Y. And the other level, local matching. Notice the global loss is a parametric, which is still called training testing inconsistency. To close the gap, we further incorporate the local loss on episodic S and Q with n classes. Instead of using parametric model, we define a non-parametric model to directly match predictions with local prototypes. Local likelihood and local loss are given in equation 3 and equation 5. Instead of calculating the similarity between the feature and global prototype here, we calculate the similarity between the feature and the local prototype, which is the mean embedding of all the embeddings that belong to the same class. And then we can combine the two objectives that is called level line objective. We propose a fourth objective, which is given in the following equation. And remark, a good metric space is all we need in metric-based feature learning, on the premise that embedding and the global weight are jointly learned via above objective. Global matching helps accelerate the convergence and explore a space that is endowed with a strong transferability. Meanwhile, local matching preserves the metric inheritance from training to testing. Okay, the other techniques we propose is contextualize level embeddings. We propose to incorporate the query set Q to refine the prototype progressively. To this end, we propose a self-attentive prototype rectification process where contextualized level embeddings are propagated from S and Q. You can look at the process from figure A to figure C. You can see that after the rectification, we can get a compact clusters. That means a discriminative metric space. Okay. Some details about prototype rectification is given in the two equations. This basically refines the prototype by considering the similarity information of the support set X and the query set Q. And to further explore the metric space and ensure the embedding is not drifted away, a residual projection stacked on top of the above attention layer given in this equation. It mimics the behavior, basically, of the transformer. Okay, experiments. We compare our methods with various state-of-the-art feature learning methods, and we can see that we have the better numbers in this table. We also conduct further analysis to determine the effects of the number of queries per class and number of classes per testing episode. Here we compare our methods and with the DFMI MCT, which is the concurrent state-of-the-art method in feature learning. So we now can answer why does ReMP improve performance. We present four scenarios covering the impact of training schedule and metric options for the demonstration. Firstly, corporate training, we only apply the four objectives. Second one, pre-train and fine-tune. We apply global loss firstly and then use local matching for fine-tuning. And third one, local matching, we only apply local objective. And fourthly, global matching, we only apply global matching. We put the results in the four tables A, B, C, and D. In conclusion, global matching stimulates a more discriminative metric space as it is observed that the accuracy in B is always higher than the corresponding one in C, regardless of the metrics. Local matching mitigates the discrepancy between training and testing as is in A and D. The reason lies in the improved transferability from training to testing, as they are being optimized toward exactly the same goal. Okay, in summary, we have presented the rectified metric propagation framework for feature learning. To cope with the inconsistent issues between training and testing in metric-based feature learning, we propose a level-aligned learning objective to close the gap, where a distributive and transferable embedding space is induced. We further enhance the equality of the prototype in the testing phase. We propose the textualized level embedding module, which progressively propagates levels to the query set based on in a repulsive self-attention mechanism. That's all. Thank you.